Good evening, everyone. So, today's session we will be discussing about week 5. We only have one live session for week 5, so we will quickly try to summarize and do some problems. So, in week 5, we have discussed about systems, types of systems, and then in the end, convolution. So, let us begin by systems. So, what is a system? What does it do? Will someone unmute and speak?
Yes, ma'am.
I am audible now.
Yes, ma'am.
So, what is a system? What does it do?
It's kind of like a black box which modifies or changes the signals.
Yes. So, a system processes an input signal and produces an output signal. So, suppose I have this input which is xt, output yt. So, what this system will do, it will take this input xt, do something to it, and then give us the output yt. So, for example, if this xt is a voltage signal, and it is given to this system which we can also call okay, let us not call anything, it is just a black box. We have a voltage signal xt, it passes through the system, and at the output I get a signal which does not have dc component. So I get signal without dc component. So this is a system. So a system processes an input signal and produces an output signal. All right. So I can denote it like this xt is given to this f system which gives me yt. So let me list some standard systems. So one is integrator. Integrator is one standard system. Then we have differentiator. We also have time shifter. So time shift can be delay or advance both, as we know. And then we have amplifier. So these are some of the standard systems. I will just quickly write down here about systems. System processes an input signal and produces an output signal. So is this clear to everyone? What is a system? What does it do? And these standard systems?
Yes, ma'am.
All right, so now let us move to types of systems. So the first classification is causal or non-causal system. When we say a system is causal, then in that system, present output depends only on past and present inputs. Future inputs are not there, either past or present or both. So for causal, present output depends only on past and present inputs. While when we talk about non-causal systems, then output at a time t depends on future inputs as well. And all practical systems that we use, they are causal because we do not know the future unless and until it is stored. So all practical systems have to be causal. All practical systems are causal. Okay, now I will give you some examples and you have to tell me whether it is causal or not. So yt is equal to x of minus t. Is it causal or is it not?
Not.
Yes, it is not causal. Why is that? Let us see. Let us take t is equal to minus 1. So y at time minus 1 depends on minus 1, which is x of 1. So this current time is depending on the future time. So it is not causal. Now let us take another example. Yt is equal to x of t plus capital T. So what about this? Is it causal or not? Anyone?
It is.
It's not.
It will depend on T. If
Yes, exactly. So if my t is less than 0, so what will happen? Let us take one example of t less than 0. Let us take it. Oh, sorry. Yeah. So let us take capital T to be equal to minus 1, just as an example. So t minus 1. Now what happens? Uh, Output at time t depends on t minus 1, that is past. So for this, it is causal. Now let us take t greater than 0. Let us take plus 1. So yt is equal to x of t plus 1. It depends on future, so it is not causal. So if in one case it is not causal, then we will say that it is not causal. All right. Now this you have to tell me according to the condition of t, whether greater than 0 or less than 0. So tell me in which case it is causal and in which case it is not. Class, anyone?
if T is less than 0, then it is causal.
If t is less than 0, then it is causal. This third one.
No, ma'am, let me think.
Yes. All right, let us again take t is equal to minus 1 for the first case. So y of this is equal to x of this. So what does it mean? If
It
my
is depending on future.
Yes, so we took capital T to be minus 1. Now we have this. We can see that it is depending on future, but if you have any confusion, then let us take small t to be equal to 0. Now what do I have? Y of minus 1 is depending on x of 0. This is past, this is future. So that means for this case it is not causal. So we will say it is not causal. Let us quickly take example of t greater than 0. What happens in that case? We have this. So now output is the future and this is like the present. So again, let us take for as an example t equal to 0. Y of 1 depends on x of 0. So this is this present at 1 is depending on 0 past. So for this it is causal, but overall we will say that it is not causal. Is this clear to everyone?
Yes, ma'am.
Yes, ma'am.
All right. Now this you have to tell me. And anyways, all these questions are from lectures, so I'm hoping you all know that. So yt is given by x of t plus x of t minus 1 divided by 2. Tell me whether it is causal or not.
It is causal.
Yes, it is causal. Why is that? Present is
Because
t.
it
Present is t. Here it is t present. Here it is t minus 1 past. So my present output is depending on present input and past input. So that is why it is causal. Now let us move to the next thing, memory of systems. So we can have two systems in this classification, one which have memory and ones which don't have memory. So we have the first thing as memoryless systems, and memoryless systems are also known as static systems. So this is just another name for that. Now what is this memoryless or static system? So for this, output at time t depends only on the input at time t. So my output at time t depends only on input at time t, neither on past nor on future, just at the present moment. So an example of such a system could be an amplifier. So this is like one example of amplifier. So this kind of amplifier is a memoryless or static system. Present output, present input, no future, no past. Now the second in this category are system with memory. The first one was memoryless, and this is system with memory. System with memory are also known as dynamic systems. So for these kind of systems, output at time t depends on the past or future inputs or both of them along with present. So one example of a system with memory is an integrator. So how do we get that? Suppose this is my signal xt. Let me call this time t naught. So if I integrate it, then this for integration I will be needing this area. So it is not only depending at time t naught but also times before that. So that is why it is a dynamic system or system with memory. Is this fine?
Yes, ma'am.
All right. So
Ma'am, can you tell this thing again?
this example, integrator
Yes,
example.
ma'am, this example.
All right. So we have this signal xt which is like this. Okay.
Yes, ma'am.
Now what I am doing is, what does an integrator do? It integrates whatever the signal comes to it, right?
Yes, ma'am.
So now this integrator will integrate this xt. So when this xt is integrated, suppose I want to find the value of the integrator at t naught. So what it will do, it will take all the values before this and then it will integrate. Integration is area under the curve. So till T naught, this is the area. So will my area depend just only on T naught? No, it will depend on these values also. So that is why integrator has memory. Is it
Okay,
clear?
ma'am. Yes, ma'am.
Okay. Now I will give you another example. I have this signal yt is equal to x of t minus 1. Does it have memory or it does not have memory?
It has memory.
Yes, it has memory. We can clearly see this present time is depending on past values. So as example, let us take t equal to 0. So y0 depends on x minus 1. Let us take t equal to 1. Y1 depends on x0. So it has memory. Another example, yt is equal to t plus 1 whole square times xt. Does it have memory or it does not have?
It has memory. No, it has not.
Yes, it does not. Why is that? Yt depends only on xt. So this is my output, this is my input. Dependence is only on the current values. Yes, these things are varying with time, but that is not part of the input. When we define memory, we define output depends only on input at time t. For static, for dynamic, output at time t depends on past or future inputs. So we are talking about inputs. Now let us take some example for this second question. So let us take t equal to 0. So it is depending on x0 only. Now let us take t equal to 1, which is 4x1. Again, it is depending on present time. Let us take y2. So again, it is depending on present time. Our present output is depending on present input. So that is why it is memoryless. All right, now next classification are invertible and non-invertible systems. So when do we say that a system is invertible? Suppose I have this output signal. If for a given output signal I can identify the input, then it is invertible. I will make it more clear in the following lines. So given an output signal, the corresponding input can be identified. So if I have a particular output, then it will map to only one input, not more than one input. Because if only one input is there, then I know that, okay, this is there. But if two, three or more are there, then I do not know which one it is. So we cannot identify the input. So if I have this system and I will say that its inverse exists, and if this inverse exists, it will be such that f inverse of yt will be equal to xt. So I had this system. Its inverse system is this, which in f input was xt, output was yt. In the inverse system, input will become the output yt, and this input of f will become output of this. So this is how we will find the inverse. I will give you some examples to make it more clear. And also we can say that the inverse operation is another system and it is also invertible. The inverse operation is another system. We say that invertible systems are lossless transformations because if given an output, I can find the input. The input is not lost. Invertible systems are lossless transformations. So we can represent it like this. This is my system. Input is xt, output is yt. Then I feed it to another system which is the inverse of this system. So I will get back xt. Are you guys able to understand this?
Yes, ma'am.
Yes, ma'am.
Okay. So, okay, if we say that the system is invertible, then we need to find that this is the inverse of the system. For invertible, F inverse needs to be found out, and if I have to prove that my system is not invertible, then this is the condition. So if there exists x1t and x2t such that f of x1t is equal to f of x2t, that is my output is same for two different inputs, then my system is non-invertible. So let us take this example. Yt is equal to xt square. So let us take yt is equal to 1. So which values of xt will correspond to yt to be equal to 1? Both plus 1 and minus 1. So for x equal to plus 1, x equal to minus 1, my output is same. So that means it is not invertible. While if we take yt is equal to xt cube, then cube does not have that quadratic kind of thing. So one unique input will have a unique output. So for this it will be invertible. Is this clear? Invertible and non-invertible.
Yes, ma'am.
Yes, ma'am.
Okay, now I will give you some examples and you have to tell me whether it is invertible or not. Sonali, are you not understanding? Like, which part do you want me to go slow, the definitions or the questions or everything? Okay. Till now, is it clear?
Yes, ma'am.
I was asking Sonali. Sonali's, are things clear? All right. Okay, so I'm giving you some questions. You have to tell me whether they are invertible or not. Yt is equal to t square times xt plus c. Is this invertible? This,
No.
yes, it is not invertible. Why is that? Let us see. Suppose I write xt is equal to, from the above equation only, yt minus c divided by t square. Okay. Now let us take t equal to 0. At t equal to 0, this xt will go to infinity. Right?
Yes, ma'am.
Now,
Ma'am,
now
but
if
in this thing, if t is equals to 0 means this whole thing will become undefined, right? X of t will tend to infinity only if there is limits, right?
my denominator becomes 0, then it will become infinity now.
Ma'am, it will be undefined. It will become infinity if t is tending to 0.
Okay.
Also, ma'am, one doubt. We can say in this that it will be invertible for all cases except t is equals to 0.
Yeah, we can say that, but in the original this definition we do not have that limit now, that t is not equal to 0. If we have that limit, then it will be, but if t equal to 0 is allowed, then it will not be. Because like, if something tends to infinity like this, then what can happen is, if I take 2xt, 3xt, and like other multiples, they will also go to infinity at t equal to 0. So for this particular yt, there are so many values which are giving the same value. That is why it is non-invertible. Is this clear? Like when something goes to infinity, then that why that is not invertible.
Okay, ma'am. Clear.
Okay, now let us take another example. Yt is equal to d of xt by dt. Is this invertible?
No.
Yes, this is also not invertible. Now, why is that? Let us see. If I take xt to be equal to some constant c, then I will have derivative of constant is 0. So, yt will be 0. So, my output is 0. If I take xt to be 2, 2c, 3c and so on, still yt will be 0. So this output when yt is 0, there are so many inputs. It is not unique. That is why it is also not invertible. Is this clear?
Yes, ma'am.
Sonali, you are understanding now? Sonali, are you understanding now? Okay. Let us take another example. Yt is equal to x of t plus capital T. Is this invertible or not?
Not.
Yes, it is also not invertible. Why is that? Let us see. If I take xt to be equal to rect t, so this is my xt, and suppose I take capital T to be 1. So I will draw x of t plus 1. So is it delay or advance? Tell me.
Advanced.
So where will my signal move? To right or left?
Left.
Yes. Plus 1 means advance. Advance means it will come earlier, so it will move to left. So it will be centered around here. These are the values. Now if I multiply them, what will I get? If I multiply these two rectangular functions, what will I get?
0.
Yes, 0, because this exits from minus half to half and this from minus 3 to half. So it will be 0. Now we find that yt is equal to 0. What happens if I take xt to be triangular of t, triangular function? So it will be something like this. Then I will do plus 1. So it will again become 0. So my output is 0 for this input also, this input also. Is it unique? No. So again, that is why this system is not invertible. Is this clear?
Yes, ma'am.
Okay, now let us move to stable systems.
Ma'am, regarding the second question you had,
Which one? This one?
the second question.
This one, derivative.
Yes, yes. No, no, no. The t square of xt plus c. The first one.
Okay, yes.
Can it be can like it's non-invertible, but can it be made invertible?
For all t equals to non-zero, it is invertible. Only for t is equals to 0, it is non-invertible.
Yes, that's right. What Jay said is right. Jay said is right. Did you understand that, Aniket? If we put the condition t not equal to 0, then it will be invertible because that is when this thing is creating problem. So
So
what I
for
wanted
t
to,
equal to 0 also, if we make a artificial stipulation that at x of 0 is some 3 or 4 maybe, then it will be invertible, right?
you mean we make some certain condition that at 0 only this value is allowed.
Yes, yes.
Yeah, maybe then we can. So what I wanted to emphasize was when we get something infinity or something 0 like this, then we can straight away say that our system is not invertible. Is that clear?
Yes, ma'am. Yes, ma'am.
Okay, let us move to stable systems. So when we talk about stable systems, we are talking about BIBO stability. That is, bounded input produces bounded output. Bounded input produces bounded output. So what does that mean? If my input is not infinity, then my output should also not be infinity. So mathematically, I can write it as for mod xt less than infinity, a stable system gives an output such that f of xt is also less than infinity. So it is critical to ensure that practical systems are unstable, because if something goes to infinity, then we do not know what to do, what will happen. It is critical to ensure practical systems are stable. And also, an invertible system is not necessarily stable and vice versa. So if I say that this system is invertible, then it is stable, or it is stable, it is invertible. No, there's no such relation between them. An invertible system is not necessarily stable and vice versa. So let us take this example. Yt is equal to t square plus 1 times xt. Is it stable? Class, is it stable?
Well, it's not visible for me. If you
Sorry?
have written anything,
What?
it's not visible for me. I don't know if it is only for me or everyone.
Others, is my screen visible?
Yes, ma'am.
Yes, ma'am, your screen is visible, but whatever you wrote, it's not visible.
It's also visible. Yt is equals to t square plus
Refresh
1
the
and
page.
xt.
Yes, I should refresh.
Ma'am, it should be unstable.
Yes, it is unstable. And why is that? Let us see. Let us take xt is equal to some constant c. So my graph will look something like this. Now xt is equal to c. So for all values of time, plus infinity, minus infinity, and everything in between, it is c, which means this is bounded. Xt is bounded. Now let us go to yt. If I put t is equal to infinity, xt at t equal to infinity was bounded. But if I put t equal to infinity here, then yt will go to infinity. So for bounded input, output is not bounded. So it is unstable. And let us also simultaneously look at the invertibility of this. So xt will be equal to yt upon t square plus 1. Here denominator can never go to 0. So that means it is invertible. So here we have an example where system is invertible and unstable. Is this clear, class?
Yes, ma'am.
Yes, ma'am. Ma'am, there was one and two questions in activity related to this.
Mm-hmm.
It was xt is equals to t into something multiply that input part. It was, I think, this y of t is equals to txt. So in that, if input would be bounded, so this t will be bounded also, right?
Yes, just like this case, let us take xt to be some constant c. So xt is bounded, whether t is plus infinity, minus infinity, whatever. This is bounded. Now let us go back to yt. If I put t equal to infinity, at t equal to infinity, xt was bounded. But if I put this, then yt will be unbounded. So it is not stable.
Oh, okay, ma'am. Noted.
Understood now?
Yes, ma'am.
This also you understood the first example?
Yes, ma'am.
All right. So let us move ahead.
Ma'am, one more
Yes.
question. It is y of t is equals to x of t into cos omega t.
This is not from graded now.
No, ma'am, it's activity.
Okay. Yt is equal to
xt into cos omega t.
cos omega t.
Yes, ma'am. Ma'am, as per me, it should not be bounded.
It should not be bounded.
Yes, ma'am. But
Why?
But cos omega t is bounded.
Let
So
her answer.
because if omega would be very large, so this cos would not be bounded.
Okay. So if I have this signal cos t, which goes on like this. So whether omega, whatever the value of this argument omega t, it will always lie between -1 to +1. Is it, Ananya?
Yes, ma'am.
So cos omega t is always bounded. Is it fine?
Okay, ma'am.
Because it will always be between -1 to 1 irrespective of the argument of cos. Now if xt is bounded and this cos is also bounded, so yt will also be bounded, right?
Okay.
Clear or still have some confusion?
I still have some confusion, but I had one question, so I'll look into it. Then I'll ask you.
No matter how large or small the value of omega is, whatever omega t is, it will be something between -infinity to infinity. And so whatever the argument is, output is always going to be between -1 to +1. That is the nature of cos. If cos is bounded, xt is bounded, yt has to be bounded.
Ma'am, if t goes to infinity, so cos infinity would be bounded.
Cos infinity would be any value, but it will be between -1 to +1, right?
Okay, ma'am.
Still confused?
Yes, ma'am. Sort of. I will clear it. Don't worry.
Okay, maybe we can discuss after the class.
Yes, ma'am.
Okay, next example. Yt is equal to xt square. Is it stable or is it not?
It's stable.
Yes. If xt is bounded, suppose it is bounded by b. So x square t will be bounded by b square. So yt will also be bounded. So that is why it is stable. And is it invertible or is it not?
Non-invertible.
Yeah, just like we discussed, for one yt equal to 1, xt could be plus minus 1. So it is not invertible. So we saw these two examples. The first one, it was unstable and invertible. Here it is stable and non-invertible. All right, now I will give you some questions and you have to tell me whether it is stable or it is not. Yt is equal to t square xt plus c. Is it stable or is it not stable?
Unstable.
Not stable.
Yes,
Not stable.
it is unstable, and let us see why is that. Let us take xt to be equal to 2. So xt is bounded for all values of t. But what happens to yt? 2 times t square plus c. If I take t equal to infinity, yt will also tend to infinity. So for bounded input, output is not bounded. That is why it is unstable. Clear, everyone?
Yes, ma'am.
Next question, yt is equal to tan xt plus c. Is it stable or is it not?
Unstable.
Not stable.
Yes, it is unstable. Why is that?
Because
At pi
at
by 2, it will be infinity,
Yes.
not bounded.
So suppose this xt plus c somehow evaluates to be pi by 2. So for some bounded value that can of course happen, right? So
Yes,
now,
ma'am. At c minus pi by 2.
yes. So that means xt is bounded, but yt at tan pi by 2 will go to infinity. So that is why it is unstable. Bounded input is producing unbounded output. Now is this stable or not?
It's unstable.
no.
Yes, it is unstable. Why is that? If I take xt to be equal to ut, it is bounded. But the derivative of ut is del t, right? Delta function. And what is delta function? At t equal to 0, it goes to infinity. So this is unbounded. So again, this is unstable. So this is differentiator. It is differentiating. Differentiator is unstable. Similarly, integrator is also unstable. Is that clear, or you want me to explain why integrator is unstable?
It's clear.
I will just quickly still do it. So
X
again,
tau, x of tau, if it is e to the power like exponential function, then the value will be infinite.
yes. So exponential is one example. And even if we take na xt to be ut, if we integrate ut, we get ramp, right?
Yes.
So ut is at equal to infinity also, it is bounded, right? But at t equal to infinity, is ramp bounded? No, because it will go to infinity. So that is why also it is unstable. Is it clear to everyone?
Yes, ma'am.
Yes, ma'am.
Okay, so another example, you have to tell me whether it is stable or not. Yt is equal to x of t plus capital T. Is it stable or is it not stable?
Stable.
Yes, this is stable. If xt is bounded, so if we delay or advance it, that will also be bounded. So their product will also be bounded. That is why it is stable. Clear, everyone?
Yes, ma'am.
Now
Yes, ma'am.
let us move to time variant and time invariant systems. So when do we say a system is time invariant? When the system description, that is the input output mapping, does not change with time. So it will become more clear with the examples. System description, which is input output mapping, does not change with time. So if f of xt gives yt, then f of x of t plus t, delayed or advanced, should produce the output correspondingly. So what I mean is, I will make this block diagram to make it more clear. I have a system. Input is xt. I get the output, which is yt. I delay yt, delay advance, yt plus capital T. And this should be equivalent if I take the input xt, I delay or advance it, and then I feed it to the system, and I still get this. So this and this are same in these operations. So this happens when it is time invariant. What happens if it is time varying? Then f of t xt is not equal to this. F of t xt is not equal to f of t plus tx of t plus t. I will give you one example. Suppose we have yt is equal to e raised to the power of minus t xt. So how we approach these problems? First, I will take my input xt. I will delay or advance it. So when
Ma'am,
I have
what is this t comma xt?
what I mean is that time taken is t, input is xt. Now time taken is t plus t, input taken is x at t plus capital T. It is just the same thing which I drew here. This is what I essentially want to say. Is this clear?
Yeah, that is clear.
Yeah, so that is what that thing is. It is just being written like at time t, x of t, time t plus t, x of t plus capital T. This f is like the system.
So, ma'am, in the right hand side of the the equality,
Hmm.
the f should not be there, right? It should only be xt plus tau.
No, this is like telling that at this time, this is the input, and this is what my system will produce. And at time t, this is my input, this is what my system will produce. So if they do not
Okay, okay.
happen to be equal, then it is time variant. Can we move ahead?
Yes, ma'am. Yes, ma'am. Understood.
Okay, so this is my example. Yt is equal to e raised to the power of t, e raised to the power of minus t xt. When we have these questions where we have to find out whether it is time variant or not, what we will do, we will take input xt, x, I will say, let's say I advance it. So x of t plus capital T. I feed this input to the system. So what will I get? Just my input is delayed. Rest of the things stay as it is. So this is what I will get when I delay the input. This is my output. Is this clear?
Yes, ma'am.
Now what I will do, I will delay the output. So if my input, delayed input, the output produced by delayed input, and just delaying the output, if they both happen to be same, then it is time invariant. But if they happen to be different, then that is time variant. So when I write y t plus capital T, I will replace this t which was in yt everywhere by t plus capital T. But in this one, what I'm doing, I'm just advancing. So that is why I just did this. So this will give me, sorry. So advancing the output gave me this. And advancing the input gave me this. Are these two equal? No. So that is why it is time invariant. Is this clear?
Ma'am, it will be invariant, right?
It will be variant now. These things, are they equal? Just a minute. Yeah. So is this equal to this?
No.
So if they are not equal, would it be time variant or time invariant?
Yes, ma'am. And time variant.
Yes. They are not equal. See, what we want is input goes to system, produces output, and we delay the output. This is one thing. And the next thing, we take the input, delay it, give it to the system, and then we get this. If these two happen to be same, then the system is time invariant. If they happen to be different, system is time variant. Is it fine?
Yes, ma'am.
Okay, next example. Yt integration from minus infinity to t xv dv. Is it time variant or time invariant? Let us try to find out. We will first advance the input. So when we advance the input, what output do we get? X of v plus capital T dv minus infinity to t. Now we will advance the output. So this t will be replaced by t plus capital T, but inside there was no t, so it stays as it is. Now when we have these kind of integrals and we want to find whether they are time invariant or not, then we try to make these variables same, and if the limits come out to be same, then they happen to be time invariant, but if they come out different, then they are time variant. So we need to do a bit of manipulation for the delayed output part. So I will make a substitution W to be equal to V minus capital T. My dW will be equal to dV. Now when V tends to minus infinity, W will also tend to minus infinity. But when V tends to T plus capital T, W will tend to, sorry, W will tend to T. W is V minus capital T. I will just write it here again. So W is V minus capital T. V is tending to small t plus capital T. So it will tend to T. So now my integration becomes X of,
W plus T.
yeah, X of W plus T dW minus infinity to T. So my limits have now become same. So I can say that it is time invariant. Is this fine?
Yes, ma'am.
So if we look at let me just go through it once again. So if we look at this case when the input was delayed and this is when the output was delayed, this integration variable, it is a dummy variable. We have this plus t
Ma'am,
here, plus t.
I have a doubt.
Yes.
So how did you find the input? Like how did you find xt plus tau?
Okay. So when we want to check whether a system is time variant or invariant, we first delay the input. When we delay the input or advance, then this plus t is basically being added. So that will be added here. This is my input. I am manipulating that right now. But when I delay the output or advance the output, then here I will replace wherever this t was there by this t plus capital T. So when I want to find out this, I will just do plus T wherever the input is there. But when I'm finding out the delayed output, I will replace this whole thing wherever T was there. Everywhere I will replace T plus capital T. But when I delay the input or advance, I will just do it here at the input only. So if there is any other time term, that I will not change when I'm doing this. Only input will be changed.
Okay.
Clear now?
Yes, ma'am.
So I was just saying, if we compare these two expressions, they are same, and that is why this is time invariant. So if I want to like kind of summarize, I will say if output depends only on input, then it is time invariant. But if output depends on input and also on some other function of time, then it is time invariant. So yeah, let us see this one. Here my output was depending on input as well as this e raised to the power of minus t, which is some other function of time. So it is time variant. Okay, I will give you some more questions. So yt is equal to xt ut. Is it time variant or time invariant? Class?
Variant.
Yes, we can. One way is to straight away say apart from input, it is also depending on ut, which is some function of time. So it has to be time variant. And I will also give you an example. Suppose this is xt. So what will yt be? Just this one, right? Because ut will clip the negative part, we will just get from 0 to infinity. Is this clear? This
Yes.
first thing.
Yes, ma'am.
Now I will advance xt. So now this is what I have. Now if I find the output, what would it be? 0 everywhere, because there's nothing after 0. Yt is this. Is this clear?
Yes, ma'am.
So now we see that delayed input and delayed output are not same. If I would have, suppose, advanced this yt, this was advance. Now I advance output. So it will be something like this. But if I advance this now, will it be same? And no. So it is time variant. Is this clear? Is this example clear?
Yes, ma'am.
Okay, next one. Yt is equal to a times x of at plus b, and it is given to you that a is not equal to 1. Is it time variant or invariant?
Varying.
Variant.
Variant.
Yes, it is invariant. Sorry, time variant. Why is that? Let us see. I first advance my output. So I advance my input. So the corresponding output will be a times x of at. For advance, I will just do plus t plus b. So this is what I am getting when I advance my input. Now I will advance my output. So I get a x. I will replace this by t plus capital T plus b. Are these two equal? No. So it is time variant. Is this clear?
Yes, ma'am.
Yes, ma'am.
If a would have been equal to 1, then you see this and this will become same. So in that case it will be time invariant, but if a is not equal to 1, it will be time variant. Clear, everyone?
Yes, ma'am.
Yes, ma'am.
Okay, let us move to next example. Yt is equal to t square xt plus c. Is it time variant or invariant?
Variant.
Time invariant.
It is time variant. First of all, if we go back to this, if output depends on input and also some other function of time, then it is time variant. So here we can straight away say output depends on input and this another function of time. So by looking at it, we can say that it is time variant. But if we want to find out, so let us do it. I will advance the input. So the corresponding output will be this. Now I will advance my output. Are these two same?
No.
No, ma'am.
Raja, are these two same?
No, ma'am.
So that means it is time variant. Clear now?
Yes, ma'am. Yes, ma'am.
Okay, next one. Yt is equal to tan of xt plus c. Now tell me whether it is time variant or invariant.
It's invariant.
Yes,
Invariant.
it is time invariant. Why is that? We can also do it by this procedure. So advance the time. Sorry, advance the input. So I get tan of xt plus t plus c. Now I will advance the output. So these two are same. That is why it is time variant. Clear?
Yes, ma'am.
Yes.
So coming back to what I told you here, if output depends only on input, then time invariant. If output depends on input and also some other function of time, then time variant. So if in xt, if it is xt plus something, it is fine. But if something is multiplied with this t, divided by t, or some function outside, then it will be time variant. So using this, you can just quickly look at, and if the function is simple, you can just quickly look at and say that no, it is variant or invariant. Is this thing clear?
Yes,
Yes,
ma'am.
ma'am.
Everyone, is this clear?
Yes, ma'am.
Ananya, is it clear?
Yes, ma'am.
Sonali, what is this trio function? Are you talking about triangular function?
Trigonometry function.
Oh, trigonometric functions. See, if I do this anywhere, even in trigonometric functions, then it will become time variant. Suppose sine of omega t, and if I have a minus sign here, this is what you're saying, right? Sonali, is this what you're saying? So this will be sine of minus omega t. So what we are essentially saying is xt is minus sine omega t. Okay. So to answer that, I would say it actually depends on the input-output relation. So if here, this is what I have. This tan is a trigonometric function, and here input is xt, here y, output is yt. So if this would have been suppose minus t, or maybe divided by something, then it will become time variant. Is this clear? Sonali, is this clear?
Yes, ma'am.
Okay, let us move ahead. Now we have linear systems. Next classification, linear or non-linear. So we say that a system is linear if it satisfies superposition principle. Linear system is a system that satisfies superposition. So superposition includes two things: additivity and homogeneity. So what I mean is, suppose xt gives me suppose xt is equal to yt, or maybe we can actually write it like this. Now additivity means that I will take x1t, which will give me y1t, xt produces yt. If I take x1t and x2t, they will produce y1t and y2t. Is this clear, or did I confuse you? Class, is this clear?
Yes, ma'am.
Yes, ma'am. It's clear.
So xt produces yt, x1t will produce y1t, x2t will produce y2t. Now, if I, do x1t plus x2t and I feed it to the system, and that happens to be equal to this, then that is what we mean by additivity. And by homogeneity, xt gives yt. If I give the input as a times xt, then it should give me a times yt. So this is what additivity and homogeneity mean, and you don't really need to go deep into what they are. Just for checking linearity, you need to remember the following: sum of scaled inputs produce sum of scaled corresponding outputs. So my system, which is denoted by f of this bracket, so a times x1t plus b times x2t should result in so a times when the system is fed with x1t plus b times when the system is fed with x2t. So if these happen to be equal for x1 not equal to x2, then my system is linear. Is this definition clear?
Yes.
Yes, ma'am.
Yes, ma'am.
Okay, so this also means that Sonali, do you have any doubt? Okay. So if this is my input, output, X is input, Y is output. If it passes through origin, a line which passes through origin, that is a linear system. But if I have some line which is a straight line, but it does not pass through origin, then it will not be linear. Is this fine? This was there in the lecture, if you could recall.
Yes, ma'am.
Now let us take some examples and see how do we check in questions linearity. So first example, yt is equal to a times x of a naught t plus b naught. Now let us take this input x1t, which will produce output y1t, which is a times x1 a naught t plus b naught. y1t is clear, class?
Yes, ma'am.
Similarly, we will write y2t a times x2 a naught t plus b naught. Now, according to what we wrote here, we have y1t, y2t, and a times of y1t plus b times of y2t. So, a times y1t plus b times y2t will give me small a into this as it is. I will now multiply b for y2t. Now I will apply the input to the system as a times x1t plus b times x2t. So this will produce output a times, this is my input output relation. So I will just replace this x with this. So what do I get?
X1 A naught T plus B naught.
X1 a naught t plus b naught plus b times x2 a naught t plus b naught. Are these two equal?
Yes.
Yes. So that means it is linear. Yes, somebody had a question. Does anyone have any question?
No, ma'am.
So this is clear, this is linear, and this is how we check linearity. Class, everyone is clear with how to
Yes.
check linearity?
Yes, ma'am.
Okay, now I will give you next example and you have to tell me whether it is linear or it is not linear. Yt is equal to d by dt of xt. Is it linear or not?
Linear.
Yes, it is linear. How do we check it? So I will apply this input a times x1t plus b times x2t. This is what I get when I apply this input. Now a times y1t is a times d by dt x1t. b times y to t is b times d by dt x to t. I add them. What I get, is it same as this?
Yes, ma'am.
Everyone, yes, a and b are constant, so they will come out. So yes, they are same. So this is linear. Okay, next
Ma'am,
one.
in the previous question, instead of a,
This
if
one,
you, yeah, the first one.
yes.
Instead of a, if you use some function of t, would that be linear?
You mean this a?
No, the capital A, yt equal to capital A.
Capital A.
Yes.
We have one. The next question is similar.
Okay.
So we have yt is equal to t square xt plus c. So this is what you were asking, Aniket.
Yes, ma'am, yes.
Now, is it linear or not? What do you think? Let us do it step by step. I will apply input a times x1t plus b times x2t. So what is the output that I will get? T square a times x1t plus b times x2t plus c. Now let us find a times y1 of t. So it is equal to a times t square x1t plus c. Let us find b times y2 of t. So b times t square x2 of t plus c. Now I add them, a times y1 of t plus b times y2 of t. So I get t square a times x1 of t plus b times x2 of t. But what else do I get? C into a plus b. Are they same?
Okay, no.
No, they are not same. So that means it is non-linear. Yes? Somebody?
No, I was supposed to say no, but I said yes.
Okay. This is clear now, this example?
Yes, ma'am.
So, ma'am, if that c was not there, it would have been linear, right?
Yes. So this is what this is now. Straight line passing through origin. This is, although the example we discussed is not a straight line, but here that constant is 0. But in these red lines, the constant is not 0. So they don't come out to be linear. And as far as the relation between linearity and invertibility is concerned, there is no such relation. You need to separately check for linearity and for invertibility. So whose question was that? Raja, right? Is this clear, Raja?
Ma'am, is all linear systems are invertible, ma'am?
No, we cannot say that. We need to check for it separately. Like we checked for linearity and invertibility, we need to check.
Okay.
Okay, now next
Ma'am,
one.
so can we say that if the system is doing range transformation without this affineness, like the constant, adding the constant, then it will be linear?
What? Please repeat.
So I am saying the system is doing some form of transformation, either domain transformation or range transformation.
Hmm.
If it is doing domain transformation, then in the previous example we saw it was non-linear. But also in the previous example there was range transformation where the amplitude was getting amplified by multiplying with a constant, and the same thing is happening here, but the range transformation is done by using this constant plus c. So if this plus c is not there, so the range transformation will also cause the system to be linear.
Yeah, basically, whether you're doing range or domain transformation, if you want to check for linearity, this is the thing that you'll have to do.
Yeah, like I am trying to like summarize the thing. So I don't have to write in every step. I don't have to calculate this. If I can observe that the range transformation is done using no constants, then I can directly say that it is linear.
I'm not sure about that. And if you want to do it quickly, you don't have to, write every step. I'm explaining you. That is why I'm writing. Otherwise, you can directly write this and this now and see. Is it
Yeah,
fine?
ma'am. Yeah.
Okay, next one. Yt is equal to real of xt. Is it linear or not? Class.
Yes, ma'am. It's linear.
It is linear. Okay, let us see. So, it will be linear.
Ma'am, what do you mean by RE? Like the real part of xt?
Yes, real part of xt. So we have a signal xt, which is a complex signal. So if we take the real part of that signal, will this system transformation be linear or not?
Ma'am, non-linear.
Yes, because okay, let us do it step by step. So
Yes.
a times x1t plus b times x2t is the input I will feed. The output will be real of a times x1t plus b times x2t. So this is what we have now. A times y1t will give me a times real of x1t. B times y2t will give me b times real of x2t. We add them, we will get a times real of x1t plus b times real of x2t. So if a and b are real, then this thing will be true. But if a and b happen to be complex, that is, they have both real and imaginary part, then these will not always be equal. So that is why it will be non-linear. Is this clear?
So, ma'am, in the question, it should have been mentioned, right? The A and B, is it real or complex?
No. This A and B is not even part of the question. This is the thing that we use now when we try to find out the linearity. So this A and B are the constants which we take ourselves.
Okay, so the scalars are taken from the field, and because xt is maybe complex, that's why the fields are also complex. That's what you're trying to say?
Even if xt is complex, but this A and B, if they happen to be complex, then they will not be equal. Otherwise, so it will be equal. Okay, let us take some example. Suppose x1t is 5 plus 3j, x2t is root 6 plus root 2j. Now, if I find the real part of x1t, what is it? Aniket, what is the real part of x1t?
5.
Yes. Real part of x1t is 5. Real part of x2t is?
Square root 6.
Yes. Now, if I multiply it with a, sum B, and if a and b are real, will we get these things to be equal, these two?
Yeah, I hope so.
Okay, let us do it. A times x1t is 5a plus 3j root 6b plus root 2bj. So I just multiplied a to x1t and x2t. Okay. Now I take the real part again of these. What will it be?
Aniket, you answer.
5a and 6 root 6b.
Yeah. And if I would separately do it like this, would it come out to be same if A and B are real?
Yes, ma'am.
But if A and B are complex, they have some real and imaginary part, then things will change, right?
Yeah, ma'am. These things will change.
Yeah. So suppose now I take A to be equal to J. So what will my real part become now? Right? Real part will become -3. Here it was 5.
Yes.
So is this clear to everyone that why this yt equal to real of xt is non-linear? It is non-linear when A and B become complex and A and B are something we take, right?
Yeah, ma'am. That's because you have said that because when A and B is real, it will be linear.
Mm-hmm.
So if someone takes A and B to be real only and not complex, then for them the system will be linear, right?
Yes.
So in question it should be
But
mentioned,
in
otherwise
when we
disambiguities will be there, right?
this A and B now, we only take A and B. So when we are checking, we have to check for both real and complex. So basically, this A and B complex in will only come into picture when you have real of xt or maybe conjugate, like when this complex kind of things come into picture, or maybe imaginary of xt. Then you have to remember to take A and B complex also, but in other cases it is not needed.
Okay, but then also, so this thing, this x1t and x2t, these are from some vector space. Specifically, these are from function spaces, right? And in vector spaces, we have scalars which are taken from some field. So some field like real numbers or complex numbers. So the field can be anything, real or complex, but it should be mentioned in the question. Otherwise, the thing gets like confusing. So that's why I'm telling.
Okay, but in general, you will not find any such thing mentioned. Uh, okay,
So
is
I
that
have to, like, I have to assume that everything I need to do in general.
yes?
So in general, A and B can be both complex and real.
Yes.
Okay.
Okay, so now this table sir also drew. I will just quickly do it. So we have this resistor, we have this capacitor, we have this inductor, and for these systems, we will just quickly write about certain properties. The first one is causality. Resistor is causal, integrator is causal, capacitor and inductor are causal. When we talk about memory, resistor does not need memory, capacitor needs, inductor also needs. When we talk about invertibility, resistor is invertible, capacitor is not, inductor is not. If we talk about time invariant, yes.
Then how we talk about the invertible case in resistor?
So if you like have a resistor in a circuit, you apply some voltage and you get some output. Okay, if we do this, then we will have a but like only one output for one input. But in capacitor and resistor, it sometimes becomes zero, and also we don't know. Uh, I you did not understand, Ananya.
Yes, ma'am.
Okay, maybe we can discuss it later. Is that fine?
Yes, ma'am.
I
Ma'am,
just
are there any like components which can be non-causal? Because like if we take the degradation of the component in account, then that component becomes non-causal. But I hope that is not the case here.
If we take some component and it becomes non-causal. Yeah, so if
I
we
am asking if there is any example of components which can be non-causal, like
okay, component.
Well, if
yeah,
something is non-causal, then that would not be like present. Right? It would
yeah, in the part it will not be part of the universe. So can we say that everything is causal?
Yeah, in general, practical systems are causal only.
Then why are we like taking this into account?
Taking what into account?
This causality in resistors, capacitors, and inductors. If everything is causal,
If you connect components in some way, like suppose I'm saying something which is a signal and I'm recording it in my phone, and so I have recorded it. Now, if I start my recording, if I make my origin t equal to 0 right when I started, then it is causal. But if I started at some later time, then some past thing is also there. So in recorded things it is there. We When we connect these components and make some circuit and other things, then that combination results in different things, but individually this is how these components behave.
okay, okay, ma'am, understood.
Now if we talk about time invariant, then all of them are time invariant and all of them are also linear. Now let us move to LTI systems. We don't have a lot of time left. So I will just quickly summarize these things so that we could move to questions.
okay. Am I hit confusion in convolution?
Yeah, I actually wanted to discuss convolution and how to do it also. Let us see how much we can do because this is the only session we have for week 5.
Yes, ma'am.
Okay, so impulse response of an LTI system. When we say impulse response of an LTI system, that means I feed the input as direct delta to the system, and when I feed the input, okay, first of all, this is valid for LTI systems only. And when I give the input as delta t, then the output that I get, that is h of t, that is known as the impulse response of an LTI system. So is this clear what we mean by impulse response of an LTI system?
Not really, ma'am. Can you explain it again once?
Okay, I have this system which is an LTI system, this block over here. This block over here, this is an LTI system. Input to this LTI system is my impulse function delta t. So when I give input as impulse, then I get this output h of t. The name of this h of t is impulse response of LTI system. This h of t is called as impulse response. Is this clear?
Yes, ma'am.
Yes, ma'am.
Input given is impulse. The output corresponding to the input impulse h of t is known as impulse response.
So, ma'am, it is just whatever will get changed by that delta t, and whatever we will get after integrating, or whatever LTI would be.
What?
So, ma'am, that HT is whatever we will get by doing the properties of delta t, and whatever the response we get after using delta t.
What I'm just saying is I have a system which is an LTI system. What is an L? Oh, I think I did not mention that now. LTI systems mean linear time invariant systems. I'm so sorry, I forgot to mention that. LTI systems are systems which are linear and which are also time invariant. Is this fine?
Yes, ma'am.
When I say a system is LTI system, I mean the system is linear, also it is time invariant. So now I have this system which is an LTI system,
and I give input to the system delta t. When I give input delta t, if I give any input, I will get some output. So when I give delta t, the output is h of t. The name of h of t is impulse response, because when I had given impulse, I got the output as ht. Is it clear now?
Yes, ma'am.
So this is what we call as impulse response. Now for LTI systems, if I just give you some input xt, and I want you to tell me the output. So for LTI systems, we have this thing called convolution which we can use. So the output for any other signal xt can be computed as yt is equal to a certain equation. So is this clear what I just said? I just said that I have a LTI system. If I give input as impulse, the output that I get is called impulse response. Is this part clear?
Yes, ma'am.
Now I have the same system. I just give any random arbitrary input xt, and I ask you to tell me the output of this system for xt. So how do we calculate that? We calculate this using this integral, which is also known as convolution. So x of tau h of t minus tau d tau from minus infinity to infinity, and you will see in later lectures that it is equal to this. This is denoted like this: yt is equal to xt. There is this star and ht. This star is known as convolution. So you have an LTI system, you know its impulse response h of t. I give you some input x of t, and I ask you to tell me the output for this input xt. So how will you find the output provided it is an LTI system? So output will be xt convolved with h of t, and this convolution is defined in the following way: x of tau h of t minus tau d tau integrated from minus infinity to infinity, and that happens to be equal to this, that is h x of t convolved with h of t is equal to h of t convolved with x of t. Is this clear what I am trying to say?
Yes, ma'am.
Ma'am, the second integral, would not there be a minus sign outside?
No, it will not be. They happen to be equal. You will see it in week 6.
Okay.
So I want to tell you, like, this is how we calculate convolution. I will just write 3 steps that we need to follow, then we will move on to example so that you can understand how to calculate this integral. So given x of t and h of t, how do we convolve them? Step 1, we will look at this, the first one. So this, I have written it again here for your reference. Yt is equal to this integral. So we first time reverse this signal h of t. We write it as h of minus tau. Since the variable here in integration is tau, so xt changes to x of tau, just the variables are being changed. Then this h of t minus tau. So how we calculate is, the variable here in integration is tau, I repeat. So we first do minus tau, then we do the time shift. So we get this. So the step 1, time reverse, h of minus tau. Second step, time shift. For each value of t, we find h of t minus tau. Now step 3, it will become more clear in the examples. Step 3, multiply and add. So x of tau is multiplied with h of t minus tau. Then all these values are taken and added. So we get the value of this integral, which happens to be equal to yt. Is this clear or very confusing?
A bit confusing.
Okay, we will take examples and then you will understand. I actually wanted to, discuss these convolution examples. So, first example, ut is convolved with e raised to the power of minus t ut. Ut is unit step signal. Okay. So, let us take xt to be equal to ut, h of t to be equal to a raised to the power of minus t ut. This convolution will give me yt. Is this fine? I took the first signal as xt, the second as ht.
Okay.
Now, let us go to the definition of ut to find my limits. So, okay, so xt is equal to ut, which is equal to 1 when t is greater than 0 and 0 otherwise, right? This is fine.
Yes, ma'am.
Okay.
Yes, ma'am.
Now let us take h of t minus tau. I will actually do this. So I can write here tau also instead of t now. This is fine. I replaced t by tau. Now h of tau will be e raised to the power of minus tau u tau, right?
Yes, ma'am.
Others are also understanding.
Yes, ma'am.
Yes, ma'am.
So now I have written h of tau. I will do time reversal. H of minus tau. So what do I get? H of tau minus tau.
Zeros minus tau.
Is that fine?
Yes, ma'am.
Now I will add t.
Can't we directly add this t minus tau to h?
T minus tau to h. Yes, we can do that, but I was showing it step by step so that everyone understands. So now I will do what did I do?
Added t.
Okay, so we have h of tau and we will do time reversal. So this was fine, right? Yes,
Yes,
na?
ma'am.
Now I want to do h of minus tau plus t, right? But here I actually intended to find h of t minus tau. So I did this reversal first. Now if I do shifting, so I have to divide it by minus 1, right?
Yes, yes.
If you recall from week 1, apart from Aniket, others are also able to recall this time shifting scaling.
Yes, ma'am.
So now I will have, if I want to find this out, I will have to divide this t by -1. So I will get minus t. So if I want to find out this signal, I have to make it this. Is this fine?
Yes, ma'am.
Okay. So now let us take this u of t minus tau. So it is 1 when t minus tau is greater than 0 or tau is less than 0 and 0 otherwise. Is this fine?
Yes, ma'am.
So also just like Aniket said now, we had this h of t to be equal to this. So here we can just simply replace t by t minus tau. Okay. And you can also do it like this. Is this clear?
Yes, ma'am.
Now let us go back to our convolution integrals. So yt is equal to integration minus infinity to infinity x of tau h of t minus tau d tau. Fine. This is my convolution integral. Here now I will replace x of tau by the function it was, that is u tau. Okay. So I do the replacement. U of tau h of t minus tau d tau from minus infinity to infinity. Now in this integral I have u of tau. U of tau is 1 only when tau is greater than 0. So the limit from minus infinity to 0 goes away. I'm left with 0 to infinity h of t minus tau d tau. Is this clear?
Yes, ma'am.
Yes, yes.
Everyone, it is clear now?
Yes,
Okay. So I have replaced x of tau. Now time to replace h of t minus tau. H of t minus tau is this function. So I will write it here. E of minus of t minus tau, u of t minus tau d tau, and the limits. This is fine, this replacement of h of t minus tau.
Yes.
Now let us go back to this u of t minus tau. U of t minus tau is 1 when tau is less than t. Otherwise it is 0. So my upper limit now becomes t. Is this fine? I just use this condition. Now I am left with this. I will integrate. So my variable of integration is tau. So this comes out. We will quickly integrate it. E raised to the power of 0 is 1. So I get 1 minus e raised to the power of minus t. Is this clear?
Yes, ma'am.
And
yes, ma'am.
and it is, since it is not there for negative values of time, so we can write it like this. Ut I will add because it is not present for negative values of time. So what I would like to tell you is, if I'm convolving yt is equal to x of t convolution h of t, then You know what will be my lower limit of yt? Lower limit of yt will be equal to lower limit of xt plus lower limit of ht. So lower limit of both xt and ht, suppose lower limit of xt is a, lower limit of ht is b. So a plus b will be the lower limit of yt, and similarly we have same thing for upper limit of yt. So upper limit of yt will be upper limit of xt plus upper limit of ht. Is the like, are you guys clear with what I'm trying to say here?
Can
Unclear?
you give an example?
Okay. Suppose my x of t lies between a1 to b1. Okay. This is fine, Ananya? Ananya?
Yes, ma'am.
And suppose h of t lies between a2 to b2. Is this fine?
Yes, ma'am.
Now what I'm saying is yt, which is convolution of ht and xt. So y of t will lie between a1 plus a2 to b1 plus b2. This is what I'm saying. Is this fine now?
Yes, ma'am.
Okay, now let us come back to the example that we took. Ut convolution e raised to the power of sorry, e raised to the power of minus tut. So what is the range of ut? 0 to infinity, right?
Yes, ma'am.
And what about the second function, e raised to the power of minus tut?
0 to infinity.
Yes, same. Now if we look at the um, like the range of yt, then it will be 0 plus 0, 0 and infinity. Is this fine? This is what I just told you here.
Yes, ma'am.
Clear now, class?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, we will take another example. Then I wanted to tell you some bonus thing, but I don't know whether we will have time for that or not. But okay, let us take the next example. So now I will be convolving rect t with rect of t. So first one I will call ht, xt. Second one I will call ht. This is fine.
Yes, ma'am.
Okay, what is the rectangular function? Someone please tell me.
Minus output of the value would be 1.
Yes. So x of tau, the first function, is 1 when tau belongs to minus half to half. This is my rect. Right? This x of tau is fine.
Yes, ma'am.
Yes, ma'am.
Now, h of t minus tau will be 1 when mod of t minus tau will be less than equal to half, right?
Yes, ma'am.
Yes.
So now tell me what will be the range of tau then for this case.
One by tau. 1 by 2 plus tau.
You have to tell me the range of tau, not t. Range of tau.
Yes, ma'am.
Okay, so I will do it. We don't have that much of time left. So this is what I have. Modulus t minus tau less than equal to half. Once it opens as positive, second as negative, right? When we solve this one, we get tau belonging to t minus half. From this one, I get tau belongs to t plus half. I mean here tau is greater than equal to t minus half. And from here, tau is less than equal to t plus half, right? Did I say it the reverse? Greater than this, and yeah. Is this fine? Everyone now?
Yes, ma'am.
Yeah. So this is the
Ma'am.
range. Yes. Yes, Satya Prakash, you were saying something?
Ma'am, I was saying yes, ma'am.
Okay. So this is what we have. Now let us go back to the convolution integral, which says yt is x of tau h of t minus tau d tau minus infinity to infinity. Now tell me, so what is the range of rect t minus half to half, right? I mean, a rect of t is 1 between minus half to half, right? And this same rect t. Now, if I want to find the lower limit of their convolution, what will it be? Using this thing that I just told you, tell me.
-1,
Yes, minus 1 and upper limit.
1.
1.
Yes. So for lower limit, I add this and this. For upper limit, I add this and this. And this is what I have. So now I know my output lies between -1 to 1. So I will first take the case when my t is negative. Then I will take the case when t is positive. Okay, now suppose this is my xt minus half to half. This is xt. Okay. Now I will take the case when t is negative. Okay. Class, are you following?
Yes, ma'am.
Yes, ma'am.
So this was x of tau. Now here let us take h of t minus tau, which was here. So h of t minus tau and t is negative. So this h of t minus tau is non-zero between t minus half to t plus half. And my t can vary as per yt. Okay. So this is what I have. Now please pay attention. If my t is between -1 to 0, then what will be my limit of this convolution integral yt?
It will be 1.
No. Okay.
It would be -3/2 to minus half.
Yeah, so let us see. When we multiply, let me speak. So this is x of tau here. This is fine. This is my h of t minus tau. If I multiply these two, so we know one thing for sure. If this thing this x of tau is 0 here, so 0 multiplied by something will be 0, right? Right now?
Yes, ma'am.
Yes, ma'am, right.
So if this is 0, so that means for negative time, my lower limit has to be minus half. Because if below this, x of tau is 0, so I will get 0. So this is my lower limit for negative time. Fine.
Yes, ma'am.
Now, when we talk about upper limit, then it will actually be t plus half, because my t is lying between -1 to 0. So if I suppose, let us take t is equal to -1. So here I will have -3/2. Here I will have minus half.
So just intersection, like only minus half is common. Now let us take t is equal to -1 is clear now.
Yes, ma'am.
Yes, ma'am.
T is equals to 0.
Now I will take t is equal to minus half. What will I get? This will become -1 and this will become 0, right?
Yes, ma'am.
So if we observe this case when t is equal to minus half, so again, this is x of t starts from minus half. This is starting from -1. So my lower limit will actually remain minus half and upper limit will not go till plus half because the maximum value it will take is half. So it cannot go beyond this. It can either be half or it can be before that. Let me repeat. So for t is equal to minus half case, my upper limit comes out to be 0. So therefore t is equal to minus half, my range becomes minus half to 0. Fine.
Yes, ma'am.
Others? Now,
Yes, ma'am.
now instead of minus half, if I take t equal to 0, so here I have half and here I have half. So basically, when my time is between -1 to 0, this becomes my upper limit and this becomes my lower limit. Is this clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, so now we have our limits for negative time. So y of t is equal to negative time minus half to t plus half, and since they are rectangular, so their amplitude will be 1 d tau. This is what I have, and when I integrate I get t plus 1. Is that fine?
Yes, ma'am.
Now let us look at the case when time lies between 0 to 1. Now my time is between 0 to 1. This is x of tau, which stays between minus half to plus half. This is h of t minus tau, which lies between t minus half to t plus half. Right now my time is between 0 to 1. If I take t equal to 0, I get minus half here, I get half here. So both are same. Fine.
Yes, ma'am.
Now let me take t is equal to half. So what do this limit of h, the second function becomes 0 and this becomes 1. Is this fine?
Yes, ma'am.
Now when we multiply for this t equal to half case, what do we get? Beyond half, this is going to be 0. So that means upper limit becomes half.
Yes.
So now upper limit is half and lower limit here was 0. For uh, back to the t equal to 0 case, this was minus half, this was half, so they were exactly coinciding. Now let us take t is equal to 1. So when I take t equal to 1, this becomes half, this becomes 3 by 2. So again, this is 0 after half. So after half till 3 by 2 and beyond, it is going to be 0 only. So what I'm saying is, now for this case, my upper limit will become half and lower limit will be this. Is it clear?
Yes, ma'am.
Yes,
Just
ma'am.
give me a moment, please.
Yeah, so coming back to t0 to 1, my upper limit was half, lower limit was t minus half. So I will calculate what happened. Yeah, so yt will be equal to lower limit t minus half, upper limit half, and rectangular functions. So multiplication will give me 1 inside this range, outside it will be 0. So I will get 1 minus t, right?
Yes, ma'am. Right.
This was when t is in this range. So if I draw, okay, if I like write it all together, then it is 1 minus t for this, and here we got t plus 1. T plus 1 when this is my range. Is this fine?
Yes, ma'am.
Now tell me, what function is this? Have you seen this kind of function?
Triangle.
Triangular. Yes.
Yes, this is triangular function. This is how it will look like. So I wanted to, tell you some kind of shortcut for convolution of two rectangular pulses. Do you want me to tell you that shortcut?
Yes, ma'am. Sure.
Yes, ma'am.
And I would request you to revisit this shortcut after watching week 6 videos, okay?
Okay, ma'am.
Okay. Okay, so the first case when I convolve two rectangular signals of equal width. So if I have minus 1 to 1. So this width is how much?
2.
2. And I have another signal. This width is how much? 2. So this is what I am talking about. When the first case, when rectangular signals are of equal width. So these two signals are of equal width. So this is case 1. Okay.
Okay,
You
ma'am.
understood now what I'm calling as case 1?
Yes, ma'am.
Yes, ma'am.
Rectangular signals of equal width. So remember, when we convolve two rectangular signals of equal width, we get a triangular function just like we got in the above example. And again, lower limit of this triangular function will be the sum of lower limit of these rectangular functions. For example, in this case, the lower limit of this is minus 1, the lower limit here is 0. So it will become minus 1. So in general, you got it what I'm saying now?
Yes, ma'am.
Yes, ma'am.
Now same for upper limit. So this also comes directly from convolution. So upper limit of this is 1, of this is 2. So 1 plus 2 gives me 3. So lower limit is the sum of lower limit of the rectangular signals, and upper limit is the sum of upper limit of the rectangular signals. Is this fine?
Yes, ma'am.
Yes, ma'am.
Okay. Now slope of this triangular function that we will get now, this slope of this line, this is what I'm talking about. So that slope will be multiplication, the amplitude of the magnitude of slope will be multiplication of both amplitudes. Suppose amplitude of this is a, this is b. So the slope of the triangular function that we will get, this slope, it will be equal to a into b. Understood?
Yes, ma'am.
Yes, ma'am.
And this one will be a negative slope, right? So it will be minus a into b. Understood what I'm saying?
Yes, ma'am.
Yes, ma'am.
Okay. Now the amplitude, that is this thing of the triangular function, it will be the multiplication of both amplitudes into the common width. I will write it down. Amplitude is multiplication of both amplitudes and that multiplied with common width. So what is the common width in this example? 2. So this amplitude will be a into b into 2. Understood?
Yes, ma'am.
Yes, ma'am.
You are understanding now the shortcut that I'm trying to tell you.
Yes, ma'am.
Yes, ma'am.
Okay, I will give you one example and then you tell me what all will be about the triangular function that we will get. So this is one rectangular function, minus 1 to 3, amplitude is 10. This is another rectangular function. So tell me what is the width of the first one
4.
and the second one?
4.
4.
It's 4,
4.
ma'am.
Same.
Sonali, I will share these notes in the G space. So this is what we have. If the widths of rectangular functions are equal, I am going to get a triangular function. So this is something what we will get. Now you tell me the lower limit of this triangular function.
0.
Yes, minus 1 plus 1, 0. Upper limit
8.
8.
3 plus 5, 8. And since this triangular is always symmetrical, so this will be like
4.
midpoint of these two things. Okay, now what will be the slope? This
60.
one. This
60.
one,
Minus 60.
yes. And what will be this amplitude over here?
120.
60, the multiplication of their amplitude. So 10 into 6 into the common width, which is 4.
4.
So I get 240.
240.
Clear?
Okay, ma'am.
Multiplication of both amplitudes into common width, which is 4. Is this fine, the shortcut?
Yes,
Yes,
ma'am.
ma'am.
Okay, now the second one is when we have rectangular signals of different width. So here it was 4, 4, right? So it could have been like this is the first one is 2, the second one is 4. So we have rectangular signals of unequal width. Okay. Second case is, what is the second case? Is that clear?
Yes, ma'am.
Yes, ma'am.
Rectangular signals of unequal width. So when we convolve two rectangular signals of unequal width, we get some kind of a trapezium. So this point I'm calling as A and this point I'm calling as B. Okay. So the first point about the lower limit. So it is same. Lower limit will be the sum of lower limits of both the signals, just like in the first case. Now similarly the lower limit will be same. Understood now?
Yes, ma'am.
And similarly upper limit will be sum of upper limit of both the signals. So first 3 points are same. Now the third point was about the slope. So when here we talk about slope, it will be slope of this and this. Okay. This will be positive and this will be negative. Fine now.
Yes, ma'am.
Yes, ma'am.
So multiplication of both amplitudes. Now when we find the amplitude, it will be this one here.
Here both the slopes are equal, right? No. The
This
magnitude of
one
the
now.
both slopes.
This one trapezium.
Yes, ma'am.
So in trapezium they are equal now. I mean the one that we get, it will be equal.
Okay.
Like this will be plus and this will be minus. Magnitude will be same.
Oh, yes, ma'am. Okay, ma'am.
Now amplitude will be multiplication of both amplitudes. Multiplication of both amplitudes and into smaller width here we will take. So in the first case, when the widths were equal, we took the common width. But in this case, we will take the width of the smaller triangular pulse. We will take amplitudes of both, multiply them, and then multiply with the width of the smaller rectangular pulse. Fourth point is clear?
Yes, ma'am.
Yes, ma'am.
Now the fifth point is regarding these values A and B that I marked here. These ones. Okay. So when we want to calculate A and B, what I will do is I will take one input's upper limit, one input's lower limit, and the other input's upper limit. So let me give you some example. Suppose this is -1, 4, this is 2, 4. So I will be getting some kind of a trapezium like this. So lower limit of this trapezium, what will be this? -1 plus 2, 1. Upper limit, 4 plus 4, 8. Now this, suppose this is 10, suppose this is 8. So this slope will be 80, 10 into 8. This slope will be -80. This amplitude will be 10 into 8 into the smaller width. This is 5, this is 2. Smaller width is 2. I will multiply by 2. So what do I get? 160. This is the amplitude here. Clear?
Okay.
Yes, ma'am.
Now for A and B, I called this A, I called this B. So what we will do is we will take once the lower limit of this. So suppose I took this -1 and suppose I took this. I will add them. What do I get? 3. Now I take this 4. I take the remaining one plus 2. I get 6. So we know that A is the lower, like the earlier value, B is the later value. So this will be 3, this will be 6. Fifth point is this clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So in fifth point, to find these values A and B here over here, I will take one upper limit, the other lower limit. I will add them. Then I will take the remaining, the ones that were left, and I will add the lower one will be A, the higher one will be B. Is this clear?
Yes, ma'am.
Yes, ma'am.
My shortcut is clear now.
Yes, ma'am.
Yes, ma'am.
Okay, I will
Yes,
give
ma'am.
you one example. You have to tell me first what will we get as a result of their convolution, and then you will have to tell me the values of the limits and other things. So this is the first one. -3, 6, amplitude 10, convolved with -1 to 4, 6. what will we get at the output? Rectangle
Trapezium.
or trapezium?
Trapezium.
Yes, we will
Trapezium.
get trapezium. Why is that? This width is 9, this width is 5. Widths are not same. If they're not same, we will get a trapezium. So we will get something like this. Now tell me the lower limit of this trapezium, this value.
-4.
-3 -1 will give me
-4.
-4. Upper
10.
limit 6,
10.
6
10.
plus 10. Sorry, 6 plus 4 upper limits will give me
10.
10. Now tell me the slope. This one.
60.
10 into 6, 10 into 6,
60
60.
minus 60.
This will be -60. Now what will be this amplitude?
300.
300.
Yes. So we will take this amplitude 10 into 6 into smaller width. Smaller width is 5. So I get 300. Now tell me this value and this value.
1.
Yes. We will take
5.
-3 plus 4. I get 1. Now the
And
remaining
5.
is 6. This is remaining is -1.
5.
So I get 5. So this is my shortcut. I hope now it is clear.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So this was about the theory part of week 5. Can we quickly do some problems? Because this is the only session we have for week 5.
Okay, ma'am.
Okay, we will quickly try to finish it. Okay. For these first few questions, you have to tell me whether the system is linear or not linear. Yt is equal to mod of xt. Is it linear or not? Take
It
your
is
time.
linear.
Do you want me to give some time to you to solve the problems, or you want me to solve it?
Give us time.
Everyone agrees with that?
Yes, ma'am.
All right, then solve it. Take 2 minutes. You remember now how to check linearity?
Yes.
We have to basically find these two values and then see are they equal or not.
Ma'am, it is not linear.
Yes, it is not linear. Anyone else also got the same answer? All right, let us quickly solve it for others also. So, first we apply the input a times x1t plus b times x2t to this system. So what do I get? Mod of a times x1t plus b times x2t. This is the first one. Now the second one, a times y1t. What is a times y1t? A times a times mod of x1t plus b times y mod of x2t. Now, are these values equal? In general, they will not be equal. For some specific values of a and b, they might be, but in general, these two are not equal. So that is why it is non-linear. Clear, everyone?
Yes, ma'am.
All right, so next question. Here also you have to tell me whether it is linear or it is not linear. This is the question. Yt is equal to xt sine of 3t. Same procedure.
Ma'am,
One,
it is linear.
yes, it is linear. Now let us do it. So when I apply this input, this is what I get. A times x1t plus b times x2t sine 3t. Now a times y1 of t is a times x1t sine 3t plus b times y2 of t, which is x2 of t sine 3t. Now we compare this and this. So are they equal? We find that yes, they are equal. That is why it is linear. Is it clear to everyone else?
Yes, ma'am.
Okay, third question. Again, you have to tell me whether it is linear or not. Yt is equal to x conjugate of t. Here star denotes conjugate. So tell me whether it is linear or not. Same procedure you will be using. Just to remind you, since conjugate has come here, don't forget to consider the case when A and B are complex. Once you get the answer, please tell me. Okay, Jay says it is non-linear. Others? Alright, let me do it and let me tell you it is non-linear. So let us do it. First, I will apply the input A times x1t plus B times x2t. So A times x1t plus B times x2t conjugate of whole. So A conjugate x1 conjugate plus B conjugate x2 conjugate. This step is clear now for this what I just wrote. Distribution of the conjugation operation.
Yes, ma'am.
Now I will take A times y1 of t and B times y2 of t and then add them. So A times x1t conjugate, A is out, like just multiplied, right? So this is what I get. Now will A will be equal to A conjugate and B will be equal to B conjugate only when A and B are real. In general, they will not be equal. So are these two equal?
No.
Yes, they are not equal. That means my system is non-linear. And let me tell you this thing. Wherever you find a real of something, imaginary of something, conjugate, then these systems are non-linear only. Okay.
Okay.
Now you have to you have to tell me whether it is time invariant or not. This is yt is equal to integration minus 60 to 60 xt dt. Tell me whether it is time invariant or not. Take 2 minutes. For time invariant, first we delay or advance the input, whatever you want to do. But if you delay input, you have to delay output. If you advance input, you have to advance output. So basically do both the things same. Do it and tell me.
It is invariant.
No, you're wrong. It is actually variant. Let us see why. So first, I will delay. Do you want me to delay or advance?
Delay.
All right. So we will delay. So first I delay my input. So I get x of t minus t naught dt from minus 60 to 60. This is what I get when I delay my input. Now when I delay my output, what I will have is x of t minus t naught d of t minus t naught. Oh, I'm sorry. I think I made some mistake. I should have written it something else, not t. It should be tau.
Then it should be
Yes,
invariant.
ma'am.
Now it will be variant, right? Yeah, I'm sorry. Because here,
Then, but in the earlier case, it was invariant, right?
yes, it was invariant because these two things will come out to be same now. D of
Yes,
t, d of t naught will be 0, so they will be same. Should I like make it another question instead of erasing? Yeah, so here they are equal. So here it is time invariant, but if it is yt is equal to x of tau d tau from minus 60 to 60. Now tell me, variant, right? Do it if you want to. Are you doing?
Yes.
Okay. Now, since my um, shall I tell the solution?
Yes, ma'am.
Yeah. So if you look at this, yt is equal to x of tau d tau minus 60 to 60. If I delay my input, this is what I will get. Now yt, when I delay white output, there is no a term of time in this integral. So this will stay as it is. Now these two will not be equal in general. So that is why it is time variant. Is that clear?
Yes, ma'am.
Yes, ma'am.
Okay, next question. You have to tell me whether it is causal or not. Yt is equal to x of sine t.
Not possible.
Yes, it is not causal. And let us see. Let us take t. Okay, let us first take t equal to 0. So y0 is x of 0. It is appearing causal. Let us take t equal to minus pi now, which is minus 3.14. So y of minus pi is equal to sine of minus pi, which is 0, right? Sine of minus pi is 0. Class, is this fine?
Yes, ma'am.
So minus pi, which is minus 3.14, is depending on the value of input as 0. So this is depending on a future value of input, right? That is why it is not causal. Is this clear? Class?
Yes, ma'am.
Yes, ma'am.
Okay. Now you have to tell me whether this is time. Anyone wants to ask anything?
Yes, ma'am.
Yes. What is it?
Ma'am, what's the real meaning behind this convolution?
Real meaning behind convolution.
Yes, ma'am.
Can we first finish the questions?
Okay.
Okay, so you have to tell me whether this is time invariant or not. Yt is given as xt times gt plus gt minus 1. So it is multiplied to it like this. For the first case, gt is 1 for all values of t. For the second case, gt is t for all values of t. Tell me the answer. Take 2 minutes for both the parts. Anyone got the answer of any one part?
I'm still solving.
What?
I'm still solving. Give me.
Okay.
Ma'am, for gt is equals to 1, it is time invariant.
Yes. And second one?
Solving, ma'am.
Okay.
And for the second case, it is time variant as it depends on t.
Yes. So how do we do this? My yt is given to be xt times gt plus gt minus 1. For the first case, gt is 1 for all values of t. So gt is 1 and gt minus 1 is also 1. So if I put that back in this yt, I will get yt is equal to 2 times xt. Is this clear?
Yes,
Now,
ma'am.
now what I told you about time invariance is this yt is just directly depending on xt. No multiplication of any other time function or anything modified in this t inside xt. So this is time invariant. And now if we move to the second case, g of t is equal to t for all values of t. So gt is t and g of t minus 1 is t minus 1. Now gt plus gt minus 1 gives me 2t minus 1. I put that back, so yt is equal to 2t minus 1 xt. Now here we see that yt is depending on this time function also apart from xt. So we will directly say that it is time variant. If you want, delaying that input and output, you can also do that. But since here we can directly see by what I told you, so this is how we will do it. Is this clear, class?
Yes, ma'am.
Okay. Now, is it clear to everyone?
Yes, ma'am.
All right. Next question. Again, you have, okay. This is yt is equal to x square t. Tell me whether it is time invariant or not. Is it linear or not? Is it causal or not? Tell me these three things. Take 2 minutes. I will solve after 2 minutes. Take your time for this. And even if you get the answer, please speak only after 2 minutes are over. You got the answer of all three parts, Ananya?
Yes, ma'am.
Okay, we will just wait for another minute and then we can discuss. Apart from Ananya, anyone else also got the answer? Okay, Jay got. Others? Raja also got. Okay. Sonali, are you doing? Okay, okay. Time is up. Shall I discuss now? We are running out of time also now. All right. So for time invariance, so do you want me to like do it traditionally by all the steps or tell you quickly or both?
For me, both. Okay.
Okay, I will tell both. First of all, for time invariance, let us first check this. So yt is x square t. So yt is just depending on input only, square of input, no other function of time or anything. So by looking at it, we can say that yes, it is time invariant. And if we want to do it traditionally, so x of t minus t naught, I delay my input. What is my output? This is what I get. Now output is delayed. When I delay the output, this is what I get. These two things are same, so it is time invariant. Time invariant thing is clear?
Yes, ma'am.
Okay, now moving to linearity. Yt is x square of t. Now I will apply a times x1 of t plus b times x2 of t. This is the input that I will give to my system. My system will square this input. So I will get a times x1 of t plus b times x2 of t whole square. Now I will apply a. I will take a times y1 of t added with b times y2 of t. So what will I get? A times x1t squared plus b times x2t squared. Are these two equal?
No.
No. So that means it is non-linear. This is also clear?
Yes, ma'am.
Yes, ma'am.
Now moving to causality. y of t is equal to x square of t. So this output, sorry, output at time t depends on input at time t. It in fact here it is neither depending on past inputs nor on future inputs. So it is not just causal, but it is also memoryless or static. So is this clear?
Yes, ma'am.
Others? So this is,
Also non-invertible.
yes, also non-invertible, right? Time invariant, non-linear, causal, and non-invertible. Because when yt is 1, xt could be plus minus 1. So last question is related to convolution. What happened, Sonali? You did not understand? Just last question. This is the last question. So this is about convolution and one of the properties of Dirac delta. So I will just quickly revise it for you. Suppose I have x of t del of t minus t naught. I integrate it from minus infinity to infinity. What is the value that you will get? Tell me this, you should know. You studied about
X of t
impulse.
now.
You studied about impulse now? Impulse function.
Yes, ma'am.
Yeah, so tell me what will be the value of this integral?
X of t now.
Yes, it will be x of t naught. Now, this was just to revise this thing because it will be needed in this question. So yt plus integration 0 to infinity y of tau x of t minus tau d tau is equal to delta t plus xt. So you have to tell me what is yt. Question is clear now?
Yes, ma'am.
Okay, tell me what is it.
Ma'am, that xt is delta t. Because only then we can apply this delta t. Right.
No, xt we do not know. It can be anything. You have to tell me what is y of t. So Nali, this is just the last question. Nothing else to be discussed after that. If you want, you can leave. If someone has doubt, we can discuss that. Do you want to try or shall I tell you the answer?
Ma'am, I don't know how to solve it.
What you?
I'm not able to understand how to solve this.
Okay. All right, so I will solve it. So let us take yt to be equal to delta t and let us observe what this integral becomes. So,
Ma'am, we can do this.
what?
Like assume y of t is equals to delta t.
Since you're very new to convolution, so it is kind of getting difficult for you, but once you get used to it, you will be able to clearly see it. So if I take yt to be delta t, y of tau will be delta tau, x of t minus tau d tau, 0 to infinity. Now what
Excuse
will,
ma'am.
yes,
Here the integration term is convolution.
yes, it is. Like I have two signals, suppose x1t and x2t. I convolve them. This is what I get. x1 tau, x2 t minus tau d tau. Okay. But anyways, even if you do not consider it to be convolution, take this. Take yt to be equal to delta t. Now evaluate this integral. So we will get delta tau x of t minus tau d tau from 0 to infinity. Now tell me what will be the value of this integral? By
0.
by the
X of t.
property by the property of impulse. Yes, please say.
X of t.
Yes, it will be x of t going to the same property that we used. This will be true when tau is equal to 0, that we will put here. So we will get x of t. Everyone is clear with this now? You remember this property now?
Yes, ma'am.
Others apart from Ananya and Jay? Diksha, Raja, Satyaprakash, Sonali.
Is it x of tau or x of t, man?
This is my integral y of t. This is my question. Integral y of tau x of t minus tau d tau from 0 to infinity. If I take yt to be delta t, y of tau will be delta of tau. And that is what I just evaluated here. Is it clear?
Okay, ma'am. What I am telling is here integration 0 to infinity
Yes.
of tau x of t minus tau d tau is equal to x of tau. I think I didn't understand.
Okay. Do you remember this property in the box? Raja, do you remember this property?
Yes, ma'am. Here it is t naught, ma'am. Instead
X
of
of
t naught, here it is tau.
No, here the value of the integration variable is not t. The integration variable is tau. See carefully in the question.
Okay, ma'am. Okay, ma'am. Sorry.
Now got it, na?
Yes, ma'am. Yes, ma'am. Sorry, ma'am.
Yeah. So now we took yt to be delta of t and we found this integral to be xt. Now if we compare this and this, we find that yt equal to delta of t satisfies this. This becomes ht, this becomes delta t. So here yt is equal to delta of t. Is this clear?
Yes, ma'am.
Yeah, so that is all I wanted to discuss. If you want, you can leave. If you have some doubts, you can ask. And I'm stopping the live stream and recording now.
Ma'am, I had doubt about this convolution.
Yes,
I have
yes. Just a minute.